Hi, I'm Nick, and in this video we're going to see what happens when we put resistors in series. That's when the resistors are connected in a line. The current that goes through one resistor has to go through the other resistor. There's no other place the current can go. Let's get started. You've probably started to notice that circuits are stacks of components. Current will flow from high voltage to low voltage. So current will come out of the 5 volts, go through the LED, go through the resistor, and into ground. I, 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 I. The current is the same everywhere. There are no other paths for the current to take. This is the definition for parts in series. They have to have the same current going through them. For instance, if I add another resistor here, the current from the LED is going to have to split. Some will go this way, and some will go this way. This resistor is no longer in series with the LED because the current that comes from the LED is splitting. It's not the same current, so they can't be in series. Here's how you can identify series connections in a breadboard. The components will touch each other in one row, and there'll be no other wires coming in from that row, inserting or stealing current. And this is how we draw resistors in series. They share one point with no other connections. Let me add some more parts in series by inserting them in the path of the current. I'll add a button and another resistor so that all the components are now in series. When I push the button, the LED is now dimmer than it was before when there was just one resistor. Why is that? Let's think about this in terms of voltage and current. We're back to our LED circuit. 5 volts to the button, to the LED, to 2 resistors to ground. There will be current through the entire circuit. The voltage across this resistor we could find using Ohm's law. V equals I times R. The voltage across resistor 1, I call it V sub R1, is equal to I, the current through the circuit, times the value of R1. The same goes for the voltage across resistor 2. That voltage is equal to I times R2. The LED needs about 2 volts to work. And when the button is pushed, it acts like a wire. It will have no volts across it. That's because we're going to pretend that wire has no resistance. When current goes through a wire, we'll just say that the entire wire has a constant voltage, so it has no voltage across it. The circuit starts at 5 volts and ends at ground. So there's a total of 5 volts. So if we start at the bottom and add up, the voltages must sum to 5. This is Kirchhoff's voltage law, KVL. And all of the currents are the same because the parts are in series. So I've got 5 volts equals 2 volts plus the voltage across R2 plus the voltage across R1, or 3 volts equals I times R2 plus R1. In this case, I'm using a 1K and a 3.3K resistor. So the equation becomes 3 volts equals I times 4.3K ohms. So I equals 3 over 4.3K equals 0.7 milliamps. That's the same thing as if I built a simpler circuit. 5 volts to the button, to the LED, to a single 4.3K resistor. These are the same or equivalent circuits. This means that when you have resistors in series, you can combine them into a single equivalent resistance whose value is the sum of the 2 resistors. I do this so that it's easier to solve for the current. Now that I know this current, I can solve for the voltage across each resistor. R1 equals 0.7 milliamps times 1 kilo ohm equals 0.7 volts. And R2 has 0.7 milliamps times 3.3 kilo ohms equals 2.3 volts. A lot of times I use this rule to figure out how to get the current that I want. This LED will be nice and bright if it has 5 milliamps through it. The LED is going to use 2 volts, so the resistor will have 3 volts. The LED uses 2 volts, and we have 5 volts total available, meaning that we have 3 volts remaining for the resistor. So to find the resistor that will get us 5 milliamps, we'll say R equals V over I equals 3 volts over 5 milliamps equals 600 ohms. But I don't have a 600 ohm resistor in my kit. Luckily, I can use a bunch of resistors in series to build an equivalent resistor. I can put 6 100 ohm resistors in series to make a 600 ohm resistor. 1, 2, 3, 4, Ground. Yay! I got the exact resistance I wanted. The LED has 5 milliamps going through it, but it took 6 100 ohm resistors in series. It took forever to build.
There's gotta be a better way.
Away with you. What I could do instead is put two 330 ohm resistors in series. That will give me 660 ohms. So now my current is 3 volts over 660 ohms equals 4.5 milliamps. That's close enough to 5 milliamps for me. That's probably the most common use of series resistors. To build a resistor that you don't have, knowing that resistors in series sum up to an equivalent resistance. For example, let's say that you have an LED that you think might be too bright. If you add another resistor in series, you'll decrease the current. You can keep adding series resistors until you get the brightness that you like. I hope you enjoyed learning a little bit more about resistors in series. Until next time, I'm Nick. Thanks for watching.